Okay, let's dive right into this. Welcome to this explainer on the absolute future of our smart homes. We are going to explore how data-driven artificial intelligence, specifically a multi-agent reinforcement learning system, can autonomously slash your electricity bills, all while balancing the heavy loads on our power grids. And listen, this isn't science fiction. It's a rigorously tested, data-driven framework that literally transforms your home into a brilliant automated energy manager.
Here is our roadmap for today. We're going to cover the smart home dilemma, predicting unpredictable energy, meeting our 4 virtual agents, Q learning in action, and finally, real-world cost savings. Let's get right to it. Section 1, the smart home dilemma, balancing demand and uncertainty. Now, what's really interesting about this whole concept is the core problem we're actually trying to solve. It really all comes down to this incredibly relatable question. Can AI slash your power bill without making you sweat? Think about it for a second. You obviously want to save money when electricity prices inevitably spike, right? And you want to maximize all that unpredictable solar power generated on your roof. But you also want your air conditioning to actually keep you cool. Balancing those wildly volatile energy costs against your everyday comfort, well, that is the ultimate paradox. For years, the old way of doing things relied on centralized optimization models, things like genetic algorithms. But they have a massive, fatal flaw. They absolutely require perfect predictions of weather and electricity prices. And let's be real, perfect foresight is completely impossible in the real world. Plus, they compute incredibly slowly. The new way? It relies on model-free reinforcement learning, and it's a total game changer. It doesn't assume perfect information. Instead, it dynamically adapts to all that uncertainty in real time, literally learning from its environment on the fly. That brings us to Section 2. Predicting unpredictable energy with the 2-part brain. To actually pull off this real-time adaptation, researchers designed a genuinely brilliant architecture. Think of it as a 2-part brain. First up, you have the forecaster. This is a neural network designed to predict future electricity prices and solar panel generation. Then, second, you have the manager. These are the Q learning algorithms that take those predictions and actively schedule your household energy use. So let's look a little closer at that forecaster. For the forecasting step, the system uses something called an extreme learning machine, or an ELM for short. It is a remarkably fast-learning feed-forward neural network. Now, it doesn't just make blind guesses. It predicts electricity prices and solar generation over rolling 24-hour windows. And to make sure it delivers highly accurate, lightning-fast predictions, this specific ELM algorithm was rigorously trained on 730 days of real-world electricity data from 2017 to 2018. It basically knows the historical trends inside and out. Moving right along to Section 3, meet the 4 agents, a day in the life. And this brilliantly illustrates how the overall system works. Because now that our AI brain has predicted the future, it has to actually take action. Instead of using one massive clunky algorithm trying to run your entire house, this system divides up the chores among 4 distinct virtual agents. We're talking about the non-shiftable agent, the power-shiftable agent, the time-shiftable agent, and finally, the EV agent. Let's break down exactly what each of them does. First up is the non-shiftable appliance agent. This guy handles the devices you absolutely cannot compromise on. Think about your refrigerator or your home security alarm. High reliability is totally mandatory here. Because of that, this agent really only has one action available to it: on. Since the load is essentially immutable and just cannot be turned off, this agent's sole focus is simply minimizing the baseline electricity costs as much as structurally possible. I mean, nobody wants to save a few pennies just to come home and find out all their milk is spoiled, right? Next in line is the power-shiftable appliance agent. This one manages your air conditioning, your heating, and lighting by choosing discrete power rating levels. What's really fascinating here is how it introduces the human element into the math. It constantly balances the cost against what researchers literally call the user's dissatisfaction coefficient. It is calculating the exact trade-off between saving you $1 today and making you sweat because the AC is set a little too low. Then we have the time-shiftable appliance agent. This one takes care of your washing machines and dishwashers. Now, unlike the AC, these appliances don't run at variable power levels. They're pretty much just simple on or off machines. So this agent's job is to quietly negotiate the absolute best time to run your dishwasher. Say shifting it from 6 p.m. when grid prices are just sky high to maybe 3 a.m. when power is incredibly cheap. The beauty of it is, you save money without even noticing the delay. Finally, we have the electric vehicle, or EV agent. This agent acts as the manager for your EV's battery charging, using discrete charging rates to aggressively hunt down the cheapest hours to charge up your car. But crucially,
And this is super important. While some theoretical systems propose sending EV power back to the grid to make a quick buck, this specific agent strictly refuses to discharge. Why? Well, because the few measly dollars you might make back absolutely aren't worth degrading a $20,000 car battery.
Okay, on to section 4, Q-learning in action, the math.
So we have our 4 distinct agents, but it really begs the question, how do they actually execute their specific tasks? I mean, how do these agents actually learn to make such complex decisions totally autonomously? How does that AC agent somehow know when saving a dollar just isn't worth the heat? Well, it all comes down to the underlying machine learning logic. So the crucial point here is how the agents manage what's called exploration versus exploitation. Imagine an agent constantly checking this massive, complex cheat sheet, a Q table. Most of the time, the agent exploits known actions. It essentially looks at its Q table, sees what schedules saved the most money yesterday, and just does it again. But occasionally, it explores. It throws a wild card and tests a completely random new schedule just to see if it somehow yields an even better outcome. It is this continuous, brilliant, self-optimizing loop. Which brings us to our final part, Section 5, Real-world cost savings and the results. Let's see how this all builds up into a real impact. When we look at the energy profile of a house, the contrast is just stark. Without demand response, a standard home has really rigid energy use, leading to massive, expensive consumption during peak hours. But flip that switch, so demand response is activated, and loads autonomously shift to off-peak periods. The system effortlessly maintains incredibly low overall consumption exactly when grid prices inevitably spike. The core wins of this research are just incredibly clear. First off, electricity costs are significantly reduced for the homeowner. Second, the system achieves insanely high computational efficiency. But using those rapid Q-table lookups we talked about, this reinforcement learning model runs absolute laps around the slow evolutionary changes of those older genetic algorithms. And third, it successfully balances that all-important dissatisfaction coefficient, which really just means the humans living in the house actually get to stay comfortable. The researchers noted that in the future, energy storage for rooftop solar PV systems will also be considered to facilitate the decision-making process. The next evolution literally integrates massive wall batteries directly into this AI loop. Imagine a home that entirely runs its own localized energy market, perfectly orchestrating the grid, the sun, and your appliances. But honestly, it leaves us with one fascinating question to ponder. If an AI is perfectly willing to let you sweat just a tiny bit to save the grid, who is actually in control of your smart home?